Hello and welcome to this quick review looking at the reactions of alkenes this time, and we'll focus on the electrophilic addition mechanism to start off with, and then look at some of the reactions that this leads on to in which this mechanism is exhibited, for example halogenation, hydration and addition polymerisation. So just to recap, a mechanism is a model that we use to try and describe what we think is happening step by step in an organic chemical reaction. So one thing we always try and do is to put a dipole on any polar bonds that are involved in the mechanism. So this gives us clues as to which direction the electrons in the bond might move. So sometimes reacting atoms or groups are nucleophiles, which means that they have a lone pair of electrons available to form a dative covalent bond. And other atoms or groups might be electrophiles. This usually means that they're positive or partially positive, which enables them to accept a pair of electrons to form a dative covalent bond. And finally, a double-headed curly arrow represents the movement of an electron pair from one place to another within the molecule. So their placement in the mechanism is very important. You have to do them accurately to get the marks. So let's look at some quick exercises. So like I've got up on the top of the screen, your independent notes and study materials should be here in front of you, because I'm not actually going to take you through all the different sort of nuances of a mechanism. I'm going to give you a couple of part mechanism examples and ask you how to think about them. So on the first one, you need to copy it onto a whiteboard or piece of paper and write where you think the next curly arrow might go. And in the second one, I've made some mistakes on purpose, and I'd like you to have a think about what they are and how to correct them. So an electron pair is moved towards the partially positive carbon atom, which forms a dative covalent bond. So therefore the more electronegative chlorine atom is now able to take both of the bonded electrons and break the CCl bond. So I'm going to do the corrected version on the left, starting with my ethene molecule. So what I want to think about in terms of my curly arrow is where are the most electrons located? Where's the most electron-rich area? So the electron-rich double bond is where my curly arrow has to start. So the partially positive bromine atom can behave as an electrophile and accept an electron pair, like we discussed a minute ago. So I draw in the curly arrow to show that happening. So this partially negative Br atom can now take the bond pair of electrons in the Br-Br bond. So we can draw that in as well. So it's really important to remember when we're doing curly arrows is that they always start where the electrons come from and point to where the electrons are going. If you follow that basic rule, you can't go wrong with mechanisms. And using dipoles indicates where the electrons are distributed along a polar bond. So in other words, if it's a delta negative end, the electrons are slightly more distributed towards that end or that atom in the bond. So what this does is it supports the position and the placement of the curly arrow. So with some electrophiles, such as halogen molecules, Br2 is a good example that we've just looked at, they don't actually have a dipole to start with because their atoms are of equal electronegativity. So what has to happen is a dipole has to be induced in the bond between them before they can start behaving as an electrophile. And the diagram shows how this happens in cyclohexene. So normally the electrons in the bond would not drift to one end or the other because they're being attracted equally by the two bromine atoms' nuclei. The proximity of the electron-rich carbon-carbon double bond in alkenes tends to repel the electron pair towards one of the bromine atoms, or chlorine or iodine, depending on the halogen that we're looking at. So what this causes is an induced dipole. So now the bromine molecule can behave as an electrophile. So what happens is the bromine molecule adds across the double bond. You can see that in the product 1,2-dibromo cyclohexane, you don't actually have a double bond anymore. So why not grab a whiteboard or a piece of paper and see if you can complete this. There's a curly arrow missing, I've left it out on purpose. So without looking at any of your notes, see if you can do this from memory. So with my curly arrow starting between the two electrons of a lone pair, it points directly at the positively charged carbon atom. Now the arrow preferably should also touch the positively charged carbon on the carbocation. And it's also acceptable to draw a curly arrow from a negative charge, because you're saying the same thing, the negative charge can be part of a lone pair. But something like that would be wrong, because the curly arrow doesn't start at either a lone pair or the negative charge. Unfortunately, that would also be wrong, because the curly arrow doesn't clearly point at anything. But this one's much better because it starts very clearly at the lone pair and it points very clearly at the positively charged carbon on the carbocation. So this time you give it a go. We want to make 1,2-diiodal cyclohexane. So pause the clip and give it a go on a piece of paper or a whiteboard for 4 marks, and I'll go through the mark scheme afterwards. So you start with the iodine molecule, and the induced dipole has to be on it already. So add the 2 curly arrows with precision, and like we said before, starting with the electrons coming from one place and pointing to where they're going in your curly arrow. So one iodine atom has already been added, and then the other has a curly arrow from its lone pair to the positively charged carbon on the carbocation. So you eventually get your final product, 1,2-diiodal cyclohexane. Okay, so let's have a look at this if the electrophile was polar, like a hydrogen halide. So if we use HBr this time, it's the same idea as before, but this time the hydrogen atom already carries a partially positive charge. Another thing you've got to think about in the second stage, where the carbocation is formed, is would the hydrogen atom always bond to that particular carbon? Let me try and illustrate what I mean by this. What happens in reality is 2 different carbocations could be formed, as you can see. You can also see that one is the major product and one is the minor product. So how do we decide which is the minor product and which is the major product? We use something called Markovnikov's rule. So if we look at the carbocation that would have formed prior to 2-bromopropane being made, you can see that there are 2 carbon atoms bonded to the central carbon where the positive charge formed. This is called a secondary carbocation, so it's more stable. In the version lower down, you can see there's only 1 carbon bonded to the carbon atom which was positively charged in the carbocation. This would have been a primary carbocation and therefore less stable, so that would be a minor product. So Markovnikov's rule states that in an asymmetric alkene where the double bond is positioned towards one side of the molecule, the halogen in the halogen halide molecule will bond to the carbon atom which has the most number of carbons attached to it. So in answers, you must always make reference to carbocation stability. So moving on to the reactions of alkenes, these do need to be memorised. This particular flowchart deals with propene. So what I'll do is I'll take each particular section of it in turn and go through the reagents and conditions that need to be remembered. So the first one is dihalogenation, the alkene reacting directly with the halogen at room temperature. So the next one is monohalogenation. I've moved to the bottom of the flowchart because I want to stay with the halogenation theme. It's probably a little bit easier to compare the two directly because we've talked about them earlier in terms of electrophilic addition. So this time the alkene reacts directly with hydrogen halide. This time it will be hydrogen bromide, obviously, at room temperature to produce a monohalogenated alkane as opposed to a dihalogenated alkane. So So moving over to hydrogenation, the alkene reacts with hydrogen gas in the presence of a nickel catalyst at 150 degrees C. This process is actually used industrially to make margarine. So in this case what we make is propane, and the final reaction is hydration, beg your pardon. So in the case of hydration, which is adding water, H2O as steam adds across the carbon-carbon double bond to produce a mixture of alcohols, and I've done two separate equations, one above each of the displayed formulae for the alcohols, so you can see that you get propan-1-ol and propan-2-ol. Now it's important to remember that all of these proceed via the electrophilic addition mechanism, and the ones where you get two different products, a mixture of products, will also have Markovnikov's rule applied as well. So for example, for monohalogenation and for hydration, Markovnikov's rule would apply in this particular case. Wherever you see a mixture of two separate products from an asymmetric alkene such as propene, you get Markovnikov's rule being applied. So to test for the presence of the carbon-carbon double bond is a very simple laboratory functional group test. You add aqueous bromine water to the suspected alkene, and the orange colour of the bromine should gradually fade to colourless as all the bromine reacts. So I'm going to play a recording of me doing this practical so you can see it live. Now in the background it's quite noisy because the fume hood is on, so I'm not going to try and talk over the sound of the fume hood. So what I'll do is I'll annotate the video as it proceeds. It's about a minute and a bit, so it's not too long. So you can see quite clearly in the case of cyclohexene, the bromine has been decolorized, so the carbon-carbon double bond must be present. In the case of cyclohexane, there's no reaction, the color remains because there's no carbon-carbon double bonds present in the cyclohexane molecule. So this could be put to use, this particular test. So for example, if you wanted to, you could perform this test on a range of different common oils, such as sunflower or coconut or peanut oil, and you can easily see which one has carbon-carbon bonds and which one doesn't. So the sunflower oil and the peanut oil have gone colourless, so that must mean they have carbon-carbon double bonds in them. So let's now move on to another application of reactions of alkenes, and this is polymerisation. So a vast range of plastic objects are made from addition polymers, as we call them, and we use alkenes to make these polymers. And I've just put a selection of items commonly found in the lab, things like a plastic bag, a plastic dropping pipette. You could make a deionized water dispenser from polyethylene or polypropylene, for example. So there's a certain convention we use to write out the process or the equation by which a polymer is made. N can stand for any number, so it could indicate up to several thousand individual monomer molecules. The monomer can be any alkene, so our monomer is our building block of our polymer. And you'll notice that the polymer is a repetition of the same unit over and over and over again. So the repeat unit is placed within square brackets. And we put a trailing bond either side, sticking through the square brackets, because they indicate the join between one repeat unit and another. So a specific example of a addition polymer might be polychloroethene, commonly called polyvinyl chloride or PVC. You'll have come across it in the black bin liners and black bin bags that you can buy in the shop. So it's a kind of a stretchy, fairly low grade kind of plastic. We'll come back to PVC a little bit later because there's something else we need to cover to do with this particular polymer. So here's a quick exercise for you. How many repeat units do you think there are in this section of polyethene? So pause the clip and come back when you're ready. Now obviously there are 5 repeat units because the repeat unit contains 2 carbon atoms just like the original ethene monomer. So the 2 carbon atoms repeat themselves 5 times in this particular section. So once we've got an item made of an addition polymer, there's a bit of a problem. They're actually very stable, so they don't easily break down in the environment. Excuse me, they're not very biodegradable. It takes about 500 to 1,000 years to biodegrade one plastic bag. So this is obviously quite a major problem. So we can either burn them to make energy. So the positive aspects to each of these techniques, for combustion it produces energy without further use of fossil fuels, and sorting and recycling allows the polymer to be used again without filling up landfill sites, like we've just mentioned a couple of seconds ago. And on the not so positive side, if you burn a polymer, particularly one like PVC, because of the presence of the chlorine in the polymer, this can turn to HCl, which is toxic, and it's released as a toxic gas. And obviously the carbon atoms become CO2, which is a greenhouse gas. And unfortunately sorting and recycling different polymers is not that easy because the polymers have to actually be separated out. So all the PVC has to go together, all the polyethene has to go together, etc., etc. You can't mix and match and then just mold them down and try and make something new because they don't mix very well with each other. So it can be separated out, but it's tricky and expensive. Okay, so this clip was obviously a bit longer than a normal quick review, but there was quite a lot to cover. So hopefully it's given you a little bit of a review of the different reactions that you need to know about. So let's do a very, very quick summary just to round it all up. So firstly, alkenes react by the electrophilic addition mechanism. Asymmetric alkenes are subject to Markovnikov's rule when reacting with hydrogen halides or water. Alkenes can be halogenated, hydrated or hydrogenated by addition reactions. We test for the presence of the carbon-carbon double bond by the addition of aqueous bromine water, and a positive result is the observation of the decolorizing of the bromine water. And finally, alkenes can polymerize from monomer molecules into polymer molecules using heat and pressure, but disposal poses some problems as the polymers are non-biodegradable, so this needs to be managed properly. Okay, so for now, thanks for listening, and until next time, see you soon.